continuation from our lecture 10 part 1, yeah, in which I prepared the videos, the video for this part 1 of lecture 10 last week. Yeah, I hope you have viewed the videos. Okay, you have viewed the videos, and I hope that you have gained something. You have learned something from these videos. Yeah, in which basically the ideas of this video is to actually few topics have been taught in part 1 of lecture 10 before. Okay, so if you can proceed with the first page, I mean this content of lecture 10, these are the topics that we have learned in our lecture last week. So up to this noise in PN and PRN photodiode. Okay, in which in last week's lecture we have learned about the noise, introduction to noise. Okay, and also the type of noise in optical receiver. Okay, and also we have learned about the noise in PN and PIN photodiode, together with the calculation of signal to noise ratio in both PN and PIN photodiode. Okay, so basically in these lectures, last lectures, these are the things that we have learned, in which I've taught you how to calculate the signal to noise ratio, the SNR. Okay, someone tried to get into the room, so let me allow the students to get into the room first. Okay, right. So this is the formulation for signal to noise ratio, which is the, okay, which is the IP squared. IP squared stands for the signal, I mean the photocurrent values, photocurrent values, and also divided by the noise, which is the mean square value of the noise induced current, so that should be the I noise. And we have learned that the I noise might be contributed from the short noise current, short noise current, and also a thermal noise current, So these are the things that we have learned last class, in the last videos posted in the YouTube. Okay. All right. So I have also learned about the bandwidth calculation, the capacitance of the detectors. All right. We did these examples on the calculation of the bandwidth and the effect on the bandwidth with regard to the capacitance. So we have learned that if the capacitance is said to be increased, so we can see a reduction of the bandwidth, which is based on these equations. So when we have an additional of capacitance value, the bandwidth will be reduced significantly. Okay. Right. So this is how I mentioned last time. I mean, just now regarding the noise that we have in the optical receivers. We have a thermal noise, also known as Johnson noise. We also have a short noise due to dark current, and also a short noise due to the quantum noise values. Okay. All right. So basically, these are the formulations for the noise current, for the thermal noise. So we have this equation, which is have relationship with the K. K stands for the Boltzmann constant. T is the temperature. B is the bandwidth, and R is the resistors or the load resistors, of the system. Okay, and this is the equation for the short noise current. Basically, this is a dark current noise. We have relationship with the charge amount E. The B is the bandwidth, and ID is the dark current value. And this is the equation for the quantum noise current. Similar with the dark current noise just now. But we have the relationship with the IP, which is the photocurrent value. All right. And following this, we have learned that this will be the noise value that we're going to have in a PIN and PIN photodiode. Okay, so we have learned this kind of photodiode, right, in chapter 5. we have learned about the PN and PIN together with the APD, yeah, avalanche photodiode. So these are the photodiode type that we have learned in chapter 5, which we're going to understand on the noise induced in this type of photodiodes and how to calculate the signal to noise ratio to this particular photodiode. Yeah, so that's going to learn in this chapter 6 basically. Okay, so for this, once you have identified the noise current in the PN and also the PIN photodiode, yeah, so we're going to, this is the formulation for the signal to noise ratio, okay, where we have the IP squared. IP stands for the photocurrent. The first term here in the denominator is your short noise, yeah, short noise is contribution of a dark current noise and also the quantum noise current, okay, and the second terms in your denominator is the contribution from the thermal noise together with the noise induced by the amplifier. Yeah, so that's why we have the Fn here. Yeah, this Fn. Yeah, sorry for that. This is the Fn. Yeah, contribution. Sorry, contribution from the noise. Sorry, contribution from the amplifier noise. Okay, right. So that should be the formulation for the signal to noise ratio for the case of the PN and PIN photodiode. Okay, and we did these examples last week, yeah, on the calculation of the noise generated in the photodiode and also the thermal noise, yeah, in the load resistor. So that's what we have done in the last week's lecture together with these examples, which is on obtaining or calculating the signal to noise ratio for these receivers. Yeah. Okay, so basically, I hope that you understand up to this stage on the calculation of noise and also on the calculation of signal to noise ratio for the case of the PN and PIN photodiode. Yeah. Okay. So for today's lecture, we agreed to continue. Let me allow students to come in the class. Right. Okay, so for today's lecture, we agreed to continue with the APD, yeah, the avalanche photodiode detector, which is the second type of photodiode. So what should be the contribution of noise? What should be the noise factors that exist in this kind of photodiode? So we have learned in chapter 5 that the difference, yeah, between the PIN photodiode and the APD is that the effect of avalanche, yeah, effect of avalanche multiplication in APD, in which it is given by the multiplication factor n. Yeah, if you can recall back in our lecture in chapter 5, sorry, yeah, in chapter 5, that we have the m. Remember, the m, the multiplication factor, is given by the current produced at the output of the APD, so I just put here SIM, yeah, divided by the initial photocurrent, yeah, initial photocurrent. So this is the M, yeah, M is your multiplication factor, which exists in the APD photodiode, yeah. Okay, so due to this M factors of multiplication, we are going to have the effect of excessive noise. Yeah, we call this as excess noise introduced in the receiver due to this gain mechanism that we have in the APD. Yeah, so the existence of this multiplication factor, or what we call as gain mechanism, will actually introduce the excess noise in your APD. Okay, yeah. Right. So for this particular case, we can write, yeah, we can write that the current noise due to the short noise, yeah, current noise due to the short noise shall be now given by these terms, yeah, which has the effect of m power of 2 plus x, yeah, m to the power of 2 plus x. Okay, because when we have a multiplication of m with regard to your photocurrent, okay, the effect will be the short noise current will also be multiplied by m. Okay, so that's why we have m squared there. Yeah, because we know that the current, the short noise current, yeah, basically is equals to square root of this mean square, right? So basically we have m here. Yeah, we have m here as the multiplication factor for your short noise current. Okay, and in addition we have the excessive noise factor, which is written to be the mx. Okay, that is why we have for the short noise current, the terms is given by 2EB IP plus ID and multiplied with m of 2 plus x. Okay, we compare this with the short noise that we are having in the PIN and PIN. Yeah, PN and PIN photodiode last time. Here we only have the short noise current shall only be given by 2EB of IP, sorry, IP plus ID only. Yeah, we don't have any M factors there because we know that in PN and PIN photodiode, there is no such multiplication factor exists. So this M only exists or only functions in the case of avalanche photodiode. Yeah, that is why for the case of avalanche photodiode, we have these factors of M, yeah, which need to be included in the calculation of the short noise current. Yeah. Okay, this particular x here will be having a value between 0 and 1.0, and it will be depending on the material used, yeah, in your photodiode. Yeah, so if you have silicon, the value will be different, yeah, for x as compared to germanium, for instance. Yeah, so depending on the value used, I mean, depending on the material used, yeah, in your photodiode. Okay, the same things happen for your thermal noise from the load resistance RL. Yeah, this is load resistance and amplifier. So it should be the same with the thermal noise equation that we have seen in the case of PN and PIN photodiode last time, in which the same terms shall be now used. Yeah, we have 4K TB Fn over L. If I can recall back, K is your Boltzmann constant, T is your temperature, B is a bandwidth, and Fn here is a noise figure. Yeah, RL is the load resistance. Yeah, so the same terms applied for the case of avalanche photodiode. Yeah, so the difference only on the short noise term. Okay, so for this particular case, since we have identified the noise, yeah, that exists in your APD, we can now write the equation for the signal to noise ratio, where the signal equation shall be now written as this. Yeah, so that should be basically the power. So we know that power shall be equals to I squared of R, correct? And again, for the case of noise, we're going to have also the terms of current squared of R. So this R can be cancelled out between the noise, between the signal power and the noise power. So we only consider the values of the current. Yeah. So that's why for the case of the signal power, due to the effect of M, yeah, multiplication factor, so we have M squared of IP squared, yeah, because from this equation, the current at the output of photodetector shall be M of IP, M of IP, okay, and since we have a squared value, so we then have M squared of IP squared, yeah, that should be the value of signal current, yeah, current of the signal. And then for the value of the noise current, we have these terms, which is obtained from the above, yeah, summation of the short noise current and also the thermal noise current. So we just sum up them together. So this can be further simplified, in which we cancel out the M squared. Yeah, so we're going to have IP squared over M power of X and M power of negative 2. Basically, these terms and these terms are the same. Yeah. Okay. Right. So hopefully you can now differentiate, yeah, the signal to noise ratio terms between the PN and PIN photodiode, and also the signal to noise ratio terms for the case of avalanche photodiode. So basically they are the same, the different only on the existence of this M. Yeah, this M multiplication factor. So we can simply use this equation also, for the case of PN or PIN photodiode by simply substituting or replacing the value of M to be equals to 1. Yeah, so if we substitute M equals to 1, the equation here will be similar to the signal to noise ratio for the case of PN and PIN photodiode that we have learned before. Yeah. Okay, hopefully you understand these issues clearly. Yeah. Right. So this will be the effect on the M. So from the equations that we have seen just now, this equation, the bottom equation there, we can see that there are two possibilities. The first one is if you are having low M, low M value, a low multiplication factor, we can see that the combined thermal and amplifier noise term will dominate. Yeah, will dominate because if we base on this equation here, if M is small, if M is small, if we base on this equation, the second terms, if M is small, these first terms can be ignored, but the second terms here will dominate. Yeah, will dominate because this is over M squared. So when M is small, when M is small, this value will be dominating. Will be dominating as compared to these first terms of the short noise current. Okay. And this will definitely improve the signal to noise ratio. Improve the signal to noise ratio because the IP will keep increasing. Sorry, these terms here will keep increasing, the IP squared, but these terms here will be constant, I can say, because the effect of M, because when you have a constant value of M, so this will be a constant value. This can be ignored. Okay, so as such, we can say that the effect of short noise can be negligible, can be ignored, and as such, the signal to noise ratio will increase. But for the case of large M, we can see that if we base on these equations here, for the case of large M, the thermal noise can be ignored. But this value will increase. Because when we have large M, this value will increase, and as such, we can say that the value of signal to noise ratio will be reduced. Will be reduced, right? Okay, so that should be the two possibilities of having low M and large M value. Remember what is M? M is your multiplication factors of the APD. Okay. So from here, we can see that if you want to find the maximum SNR, maximum SNR, we need to find the optimum value of multiplication factor M, in which this is through the experiments. This is the ratio, the ratio between the short noise. This is the short noise current that we have seen just now, the equation of the short noise current. And this is the equation for the thermal noise current. Thermal noise current. We can see that by experiment, this is what have been proved, before, that the optimum value of the M can be obtained if we have the ratio between the short noise current and the thermal noise current will given by 2 divided by X. So if we have this ratio between the thermal noise, between the short noise and thermal noise, which is 2 over X, we can say that the M value is said to be optimum. Okay, so I repeat again. The first terms here is the value obtained from the short noise terms here. Okay, the short noise terms, the first term here on your denominator. And the second terms here is the terms from the from the thermal noise terms of your denominator. So the ratio between them shall be equals to 2 over X, such that the M value shall be then optimized. Shall be the optimum value of the M. Okay. So by this, we're going to have that the optimum M. By solving this equation, we can see that the optimum M to the power of 2 plus X shall be given by 4 kT Fn divided by X times E IP plus ID of RL. So basically, this should be the equation that shall be used if you want to find out what should be the optimum value of the multiplication factor M that will give a maximum signal to noise ratio value for the avalanche photodiode receiver. Okay then, hopefully you understand, yeah? Okay, this will be the equation that shall be applied. I repeat again, this should be the equation that shall be applied to find the optimum value of multiplication factor M with respect to different X. Yeah, X is your factors, yeah, excessive noise factors that we have learned in previous slide. Yeah, that will give us a maximum SNR value for the avalanche photodiode receivers. Yeah. Okay, so this is the graph that shows the effect of SNR improvement with regard to the avalanche multiplication factor M, yeah, the factor of M, and effect on the X values, yeah. Okay, hopefully you understand about this signal to noise ratio calculation for the APD, and also how to calculate the optimum value of the M that will give us the maximum SNR, yeah. Okay, so this is the comparison of the APD with regard to the different material used. Yeah, we have a silicon, we have a germanium, we have the indium gallium arsenide. Okay, these are three materials used in your APD fabrication. The comparison is to be based on the wavelength range. Okay, so these are the wavelength range. Okay, so this might help you in your assignment. Yeah, because you have to be based on specific data sheet, yeah, of the receivers. Okay, so you have to find out the data sheet for the receivers that can be used, yeah, in solving your assignment questions. Okay, so for instance here for the wavelength range, if you want to use at 1550 nanometer, you have two options, either to use the germanium or you can use the indium gallium arsenide photodiode. Yeah, the avalanche gain, the M, we have a very high value for the silicon and germanium as compared to indium gallium arsenide, which is very small. The dark current, which is basically its unwanted value, is small for the case of silicon as compared to germanium and indium gallium arsenide. Okay, and the rise time, okay, this will be learned in chapter 7 later on. Yeah. Whereas for the gain or the bandwidth, we have very high bandwidth for the case of silicon, yeah, and also for the indium gallium arsenide as compared to GE or germanium, which is very small. Okay, and the bias voltage is the reverse bias, the voltage that shall be applied in your APD. So for the silicon, it requires a very high, yeah, requires a very high reverse bias voltage up to 400, yeah, as compared to germanium and indium gallium arsenide. Yeah. Okay. So this is a very short comparison between the APDs depending on the material used, yeah, in the APD fabrication. Okay. So let's have a look at these examples here to test our understanding on the topics of noise and signal to noise ratio in your APD receivers. Yeah. Okay. So we are given here in this question a silicon base APD, which is operating at 300 Kelvin, and the load resistance of RL of 1000 ohm. So we are given that the responsivity, yeah, responsivity R is 0.65 ampere per watt, and the X now is given by 0.3. Okay, so R, I hope you can still recall, yeah, from chapter 5 that R, so sorry, the R, okay, the R shall be equals to the current. Yeah, current. I'm not sure what's the problem with this. Sorry for that. Yeah. Okay. Okay. R basically is given by the current divided by the power. Yeah. Current, which is photocurrent, divided by power. Power is the incident power on your photodiode, and the IP is the produced, yeah, or generated photocurrent by this particular incident power. Yeah, so that should be the responsivity. So we have learned about this responsivity definition in chapter 5. Yeah, hopefully you can recall back in case you forgot about these responsivity issues. Yeah. Okay, so given here that leakage current is negligible, so leakage current is similar to dark current, yeah. So which means that your ID is equals to 0 lah, yeah. ID is 0, yeah. Leakage current and dark current is similar, yeah. So ID is 0 in this case. Okay, so we are given for the first question that 100 nanowatt of optical power said to fall on the photodetector. So the question is, what should be the optimum avalanche gain M? So we need to find out what should be the optimum value of your multiplication factor M. Yeah, this is the requested answer. I mean, requested things to be solved in these questions. Yeah. Okay. So for this particular case, you have to use the equation that we have learned in the previous slide. Yes, yeah? So I solve the question one by one. So the first one is to find the optimum M value. Okay, so for this particular case, from the equations that we have seen in the previous slide, that give us the definition, the equation for the optimum value of M, which is optimum M power of x plus 2 shall be equals to 4kt. Sorry, this is disturbing. Yeah, this line is very disturbing. I'm not sure why. Okay, shall be equals to 4kt divided by the x of E RL, the load resistors, multiply with your with your, I can say this is your IP, I believe. Yeah, your IP. Yeah, because I'm sorry about this. Sorry about this disturbance. Yeah, I'm very sorry about that. Okay, so we have here as x of E. We have the RL, and that should be the IP, I believe. Okay, and this is the power of 1 over x plus 2. What is this? Yeah, what is this line? Why it keep come out? Okay. I see. Okay, never mind, right? So, okay, this is x plus 2. So this is based on the previous equation that we have here. Sorry, this is the equation. Okay, I'm using this equation here. Okay, in which ID is 0, yeah? ID is 0. So we just have IP there. Okay, and we have 4kt of Fn. And in this particular questions, we assume that Fn equals to 1. Yeah, because there is no information given on this noise figure. So we assume that Fn value shall be equals to 1. Yeah. Okay, that should be the equation used. And for this, we substituting all the terms, the K, the T is 300 Kelvin. K is a Boltzmann constant, for 1.38 times 10 negative or 23. X 0.3. E is a charge amount, 1.6 times 10 negative 19. RL is the load resistance of 1000 ohm. And IP is to be obtained. We can find IP based on this relationship between the responsivity and the power. So we have IP shall be equals to R multiplied by P, which is 0.65 multiply with the P, which is 100 nanowatt, yeah, which is the incident power. Okay, so that should be the IP. So by substituting all of this information here, we are getting the optimum M value shall be equals to 42. Yeah, you can substitute all the given information in these terms here. Sorry, I missed something here. There is no more x power of 2, yeah? No more x power of 2 because we have bring this power to the right hand side. So that's why we have 1 over x plus 2 there. Yeah. So we have the M optimum should be equals to 42, which is obtained by substituting all the parameters given in the questions. Yeah. So that's how you obtain the optimum M. Okay, hopefully you understand about this first part of the questions. Yes, I'm going to erase this. I'm going to proceed with the second part of the questions. I'm very sorry about this disturbance. Yeah, I'm not sure why. Okay then. So let us proceed with the second part of the questions. Okay, the questions here is to find the SNR if the B is equals to 100 megahertz. Yeah, right. So this should be related to the equation of calculating the SNR for the APD. If I can go back to this slide, we're going to use this equation here, yeah, for the APD, the M squared IP and so on, yeah. So we have to use this equation to find the SNR value. Okay, so we are now using the optimum M that we have obtained in the first question just now, in which the M shall be equals to 42. Okay, so we're going to have that the SNR, we're getting worse, yeah? I see. The SNR shall be equals to M squared IP squared divided by the 2EB, yeah, IP plus ID, yeah, it write it for you then. Multiply with M to the power of 2 plus X plus the 4K TB over RL multiply with Fn. Okay, so this is equation from the slide that we have learned just now. So what you have to do is you need to substitute all the information in which we are going to have the M shall be equals to 42 power of 2. The IP is based on the previous method in which we substitute by, yeah, IP shall be equals to R multiplied by P, yeah, which is R is your responsivity, P is your incident power. So we have RP squared, yeah, RP squared, okay, divided by this all the information where we have a 2 EB, yeah, E is the charge amount, B is bandwidth, it is given by 100 megahertz, yeah. So we're going to have 100 times 10 power of 6, okay, that should be the bandwidth, and the IP, we only have IP here, we don't have ID because ID is 0. So we have RP as a substitution for the IP there. M is 42, power of 2 plus X, so X 0.3, so we have 2.3 value, plus the 4 KTB, which is 4, K is Boltzmann constant, you can write on your own, 1.38 times 10 of negative 23. T is the temperature of 300 Kelvin, okay, and your B is 100, sorry, it's getting worse, I'm not sure why then. Fn is 1, because there is no information given, so we assume Fn is 1, and as RL is equals to 1000 ohm, yeah, 1000 ohm. So by solving this, yeah, you are going to get the SNR, yeah, SNR, but the SNR that you are going to get is in linear value, yeah. So to find the dB, SNR in dB, you have to write the 10 log of the obtained value of SNR from this calculation, yeah. Right, so that's how you obtain the SNR in dB for this second questions, yeah, of this problem. Okay, right, so hopefully you understand about these examples clearly. I'm not sure about this problem, sorry about this disturbance. I'm not sure why. Sorry for that. So it's not that responsive now. Okay, never mind. So for the third questions, we need to compare the SNR obtained from the APD with the SNR that shall be obtained from the PIN photodiode. Okay, so for the PIN photodiode, it should be easier because we don't have any effect of M. Okay, so from this number 2 just now, if I can write for you, just now we have the SNR for the APD, yeah, is 659, in which in dB it is equals to 10 log of 659 shall be equals to 28.2 dB, yeah. That should be the value for the SNR for the case of APD. For the case of PIN photodiode, okay, we are getting that the value, for the PIN photodiode, the value of M shall be equals to 1. Yeah, M equals to 1. So by using the SNR, yeah, we're going to have the SNR value shall be written simply to be IP squared over 2EB of IP plus 4KTB divided, this is 4KTB, yeah, divided by RL. Yeah, we only have these terms here for the case of SNR of PIN photodiode. And by substituting all the informations, we are going to get that SNR shall be equals to 2.3. Yeah, and in dB it should be 10 log of 2. Wow, getting worse lah. What happened? I'm sorry about this, yeah. Whether you have to face this kind of problem during our lectures. Okay, so in dB it should be 10 log of 2.3, which will give us about 3.5 dB only. Okay, so this is the SNR that you're going to get for the case of PIN photodiode, and we compare this with the SNR that shall be obtained from the APD, which is very much difference, yeah. So SNR for APD is very high, 28.2 dB as compared to a very low SNR for the case of PIN photodiode. Okay. Okay, any questions up to this example?
So far, okay, Doctor.
Okay, yeah. Okay, so let's have a look at these examples here. Okay, on the case of, again, on this APD, avalanche photodiode still. We are given a APD of X of 0.3, the capacitance of 5 picofarad. We have zero dark current, negligible dark current, yeah. So from here, we can see that the ID is 0. Yeah, the ID is 0. Operating exposed detection bandwidth of 50 megahertz. So B is 50 megahertz. Okay, 50 megahertz. Photocurrent gain is 10 power negative 7 ampere. So this is your IP. Yeah, that should be your IP, the photocurrent value. Temperature is 18 degrees. So in Kelvin, it should be 273 plus 18, which will give us about 291 Kelvin. Okay, that should be your T. Okay, and determine the maximum SNR improvement between M equals to 1 and M equals to optimum M, assuming all operating conditions are maintained. Okay, so I can see that this is about similar to what we have learned. Similar to the previous example. Yeah, because we need to see what should be the improvement of SNR when we have M equals to 1. So this is similar to your PIN photodiode actually. and this is for the case of optimum M value. Okay, so for this particular case, what you have to do is that you are given few informations. Yeah, few information: the capacitance, the bandwidth, the temperature, and also the IP. Okay, but if you base on the equation, yeah, on the SNR, if you can write the SNR equation for you, SNR, that should be equals to, this is for the case of PIN photodiode, yeah, IP squared over 2EB of IP, because we ignore the dark current, plus 4KTB over RL, multiply with your Fn, which is your RL, yeah. Okay, in this particular case, you assume that Fn equals to 1, yeah, because no information is given on the Fn or noise figure, so we assume that Fn equals to 1, okay, equals to 1. RL is unknown, am I right? We don't have any information about RL. So we need to find RL. We need to find RL from these problems, in which RL can be obtained from the equations that relates the bandwidth and the capacitance and also the load resistance. Yeah? So we have the bandwidth B equals to 1 over 2 pi RL multiplied with the capacitance C. Okay, yeah. So this should be the equation that enable us to find the RL because bandwidth is given, C is given, capacitance is given, so we need to find the RL based on this equation. So from here, you can find that RL can be calculated, end up you're going to have RL should be equals to 635.5 ohm. Yeah, so that should be your load resistance obtained. Yeah, okay. So from here, you can write. So if you can write for you for m equals, this is for m equals to 1. Yeah, this is for m equals to 1. Yeah, which is similar to the PIN photodiode terms of signal to noise ratio. So you're going to have this as equals to, yeah, when we substitute all the information is given, IP is 10 power negative 7, the B is 50 megahertz, so the KT can be obtained, is given here, and RL has been calculated before. So end up, you can calculate that the signal to noise ratio shall be equals to 7. Sorry about this. Okay, so the signal to noise ratio shall be equal to 7.91, and in dB it is equals to 8.898 dB. Yeah, this is in dB. Okay. Okay, so need to do the same things for the case of M optimum, but you need to find out what should be the optimum M before we can calculate the signal to noise ratio. So again, we are using the equation for the optimum M. Yeah, the M optimum shall be based on the 4 KT divided by X of E IP RL. Okay, and we're going to have this as 1 2 power of X. Yeah, 1 over 2 plus X power. And we are going to get that the optimum M by substituting all the informations, including X of 0.3, you're going to get that the optimum M value shall be equals to 41.54. Okay, so that should be your optimum value of M obtained. So from here, you need to substitute this optimum M value in the calculation of signal to noise ratio, yeah, which is based on these equations. Sorry, yeah, I have to go back to this slide. Based on these equations here, okay, these equations down here, yeah, for the case of APD. So substitute M of optimum just now, which is 41.54. So all information is unknown, okay. So you are going to get that for this particular case of SNR for the optimum M, you are going to get the value shall be equals to 1.78 times 10 power of 3, yeah, for this M optimum. And in dB, it is equals to 32.50 dB, yeah. So that should be the value for your SNR, yeah, for the case of optimum M value. Okay, so we can compare the value of SNR for the case of M equals to 1, which is about 8.98 dB only, yeah, which is a typical value for the PN and PIN photodiode. But for the case of optimum M value, for the case of APD, the SNR has been increased tremendously up to 32.50 dB. Okay, so hopefully by now you can differentiate the signal to noise ratio value for the PN, the PIN photodiode, and also the signal to noise ratio value for the avalanche photodiode, and methods or techniques on how to calculate this signal to noise ratio. Yeah. Okay. Right. I'm not going to do this example. So I hope that you can try to solve this on your own. So if you find any difficulties on solving these questions, you can always PM me for further discussion. Yeah. Okay. So with that, I end up we have wrapped up the lectures on chapter 6, which is on the noise in optical receivers. So tomorrow's lectures, we're going to enter chapter 7, which is the last chapter for our syllabus, yeah, for our course, which is on the system design. Yeah, so the system design lectures will be about 4 hours. So 2 hours for tomorrow, and we're going to have the rest of 2 hours for next week's lecture. So basically, I can say that our lecture will be wrapped up, yeah, by next week. Okay, so is there any questions on our lecture 10 before we end the class today?
No, doctor.
No questions. Yeah? But still, if you have any questions, any queries, please don't hesitate to contact me, yeah, for further discussion. Okay, so I'm going to meet you again tomorrow at 9 o'clock for part 1 of chapter 7. Yeah, lecture 11, part 1. So I put these lectures in our Google Classroom, so you can try to